Okay, welcome everyone. So it's a pleasure to announce the first QGI Seminar of 2021. So we have a speaker all the way from Canada, Lampros Lamprou, and he's gonna lead a discussion on a talk that he gave previously that is called Inside the Hologram. So I'm sure everybody knows the format, the new format. This is heavily be more of a question and answer, more of a discussion rather than a normal talk. So please feel free to interrupt Lampros at any point and just take it away.
Right. Well, thanks for having me. It's a great pleasure to be here at 6 a.m. my time. So yes, I don't know how this will work. So my plan is to start talking, prepare some context for this work, which is some work with Daniel Jaffers, which was published earlier late last year. And there is some ongoing work with both Daniel and Jan, which I don't know if I will get to. It's still in progress. So my plan is to start saying a couple of things, set up the stage, and allow enough space and time for you guys to interact with me, ask questions. And I'm open to take the conversation wherever it goes, if it goes somewhere. Otherwise, I'll just continue talking at a slower pace than usual. That's the plan. And forgive me if you all watch the talk and you hear some things the second time. It's, I guess, what can I do? So the general idea is a perspective on ADS-CFT that I kind of like to use is that the duality gives us two different ways of looking at this same physical system. Two different perspectives on the same physical system. One is the outside perspective of the experimentalists who built n equals 4 per Young Mills in their lab. And the other one is the perspective of an internal observer, a subsystem of n equals 4 per Young Mills, some sort of coherent semi-classical probe, from which perspective somehow the physics of the system is that of a gravitational theory with some quantum fields on that dynamical spacetime. Now we understand a lot about how to kind of formulate the physics of this quantum system from the outside. It's just the traditional quantum formalism using CFT technology and so on. But there are several questions about gravity that require us to kind of jump inside the hologram, to switch to the perspective of this internal subsystem. In fact, the question of bulk reconstruction is essentially one of that. It's precisely this. So this is a kind of conceptually confusing thing to do. This switching of reference frames in quantum mechanics, and that's what we try to kind of initiate some sort of formalism to address this type of questions. And the motivation is black holes. There are good reconstruction techniques when there are no black hole horizons. They have their own issues in specific situations. But the problem with black hole horizons is that there are no known, or at least there are not known ways of reconstructing degrees of freedom behind the black hole horizon that are free of any issues, conceptual or technical. Part of the problem is the fact that behind the horizon region is causally inaccessible to the outside observer. If you send something in, it'll just fall in and then never come out classically, or quantum mechanically it'll come out, but in a very scrambled form later on. But if you jump in a black hole, you will definitely see something. And we would like to kind of learn how to ask that question. How do I propagate degrees of freedom in your reference frame, the infalling observer's reference frame? If I have some kind of operator out here, which I know how to reconstruct using traditional HKLL. You know, it's some sort of reconstruction which uses the equations of motion to rewrite this local operator phi in terms of boundary degrees of freedom. And if I also have a probe that kind of propagates along this world line and falls in the black hole, what is this time evolution operator in the reference frame of this infalling probe? What's the operator that can take this guy and propagate it inwards? The proper time generator, if you will. And various questions. So yeah, so there's various ways of asking this question, but this is ultimately what we want to get to. This is the ultimate goal. Identify, given a probe and in a particular dynamical system in a particular state, given a probe, what are the rules for building from first principles in the CFT that operator, which I will call H proper time, that propagates the system or degrees of freedom near my probe along this probe's world line. So if you will, it's kind of the experimentalist approach, it's kind of the operational approach to probing the black hole interior. And of course, this would access to such an operator, of course, would give us a reconstruction of the interior, which ideally would resolve certain puzzles that exist, conceptual puzzles about this interior reconstruction. One of which is the following, and this puzzle was actually part of the motivation for this work. If you have, it's a puzzle that is both for both for single-sided and for two-sided black holes, but it's most clearly stated for a two-sided setup. If you start with a thermofield double between two CFTs, the right and the left CFT, you're expected to describe holographically this kind of short wormhole between this two-sided ADS wormhole. Now, if you introduce some kind of probe here, this after a finite proper time, this probe will be behind the horizon. So if I take some operator over here, as we were discussing before, some operator that I reconstructed from, that is an entirely right CFT operator, some phi r, which is built out of right CFT degrees of freedom, and I propagate along this world line, then after a finite amount of this type of evolution, I'll be behind the horizon and able to receive signals from the left. This means that phi of r evolved with this proper time type of evolution, will not commute with some subset of the degrees of freedom of the left. And the reason why this is a little puzzling, at least it has been puzzling to me conceptually, is because the two CFTs are decoupled dynamically. They're in an entangled state, but the two CFTs are decoupled. So a degree of freedom on the right will always, an operator on the right will always commute with all operators on the left, and no amount of boundary time evolution will ever make it not commute with the operators on the left. It will always remain a right operator. Yet, somehow, for certain states, as a result of the entanglement present in the initial slice, this operator, this proper time evolution we're looking for, couples left and right, the left-right systems, mixes the two algebras. So the mere presence of entanglement, after switching reference frames to this internal infalling reference frame, translates to a dynamical coupling between left and right. And this is something that I find. Yes, yeah, go on.
Okay, I have a question.
Please,
so in principle, till the moment it crosses the horizon, you should be able to evolve it with the right Hamiltonian, right?
Absolutely.
I mean, but that would correspond to evolving for an infinite time, right? Like if I think about time foliation, time slices that go all the way to the bifurcation surface, right?
Right. Yeah.
I mean,
infinite boundary time. That's right.
Boundary time. Yeah. Of course. Yeah.
So, but it's finite proper time.
Yeah, of course. So basically, like if you evolve on the boundary and only on the right boundary, you would just evolve for an infinite time, and things would look perfectly normal.
Yeah, you just never cross the horizon in that case.
You just never cross the horizon.
Always stay on the outside. Right.
So basically, you're asking a question for an interpretation of the evolution operator that's gonna be defined probably in HL and HR. That's going to allow you to cross the horizon, right?
Yeah, so it's as you say correctly, in order for this to be, so as you say, if you only focus on the boundary evolution, clearly you just never cross the horizon and there's no puzzle, right? You never probe the interior. And that's fine. On the other hand, if you are ever crossing the horizon, just by and you can trust this kind of diagram that I'm drawing here, because you may say it's just not how black holes work, and this expectation from GR is just not right. But if we do trust that this expectation is right to some degree, then clearly that operator H proper time has to be a two-sided operator. It has a couple left and right. The puzzle or the conceptual kind of confusing aspect of this is that in what sense does the clock of a right CFT degree of freedom know about the existence of the left? In what sense the internal clock, you were this observer here who falls in the black hole was built out of quarks and gluons of the right CFT. Right, he's made out of an excitation that's localized in the right CFT, which is dynamically decoupled from the left. So, in what sense does the internal clock of this guy get generated by an operator which inevitably mixes it to the left with the left? That is kind of the conceptual puzzle. I'm not saying it's a contradiction. It's not a contradiction. It's not a puzzle like the information puzzle. It's a puzzle of what are the rules, whatever the rules are, for switching to that internal perspective. Somehow entanglement between left and right is key, because that's the only way that a right excitation can know about the left. So somehow the entanglement gets translated to this coupling between left and right in this infalling frame.
So I have one more question on this. I mean, I watched your talk, but I couldn't really distill this part from your talk. Maybe it's in the paper. So do you expect something some very sharp change in the operator describing the evolution to occur after the proper time ticks? I mean, like after you reach the horizon? So like that's where this this commutator is going to be becoming non-zero, right?
Yeah, so that commutator with some left some left operator being non-zero is, I would call it as a sharp change. Now, of course, I would like to have. You mean in the? Maybe I'm not appreciating the question though. Maybe you're referring to whether I have.
Whether you see this in your framework, maybe just to jump in ahead.
Yeah, so I have a comment on that. Because I really don't know to what degree I should trust that you guys have watched the talk, so I don't want to jump to that. But yes, so I can discuss this part actually, but probably I should first perhaps kind of comment on what that framework even is before I say how this type of puzzle seems to be addressable in that framework. But yeah, so the point is that in the framework I guess I'm supposed to talk about today. Our proposal for what this generator of proper time is just doesn't have that problem. The flow that it generates naturally mixes left and right in this particular situation. So that kind of goes away. If you trust the principle or the rules that I will present you, then this problem is not there. And so I would say that our proposal does not suffer from this kind of confusing aspect, if you trust, of course, our reasoning. And yeah, but I will get there. Perhaps in a little bit, I want to perhaps talk about the formalism a little bit more first.
Am I allowed to ask a related question?
Yeah, go ahead.
Sorry. So my question is there a version of this for one-sided black holes? Because, you know, you could say that you have a one-sided setup, like a black hole that forms from collapse, or, you know, an eternal black hole, but it's one-sided. You would eventually run into some similar confusion, because the boundary time evolution still would not see anything fall into the black hole. Nevertheless, even there, you expect that some kind of proper time should evolve you inside. And and so there's no left CFT in this case anymore, but still you expect somehow that there is some bizarro operator or time evolution that should nevertheless propagate the local observer into the black hole in that case as well, no?
Yeah, that's right. Yeah, so so what the framework that I will present, first of all, I should clarify what is known and what is not known. So we developed a framework for extracting physics in that internal reference frame, which we know works, and we understand how it works in cases where I'm not falling in the black hole. When you fall in the black hole, there are some observations one can make by applying that formalism, but it's not a done deal yet, and that's exactly why Jan and Daniel and I are still working on kind of refining this proposal for falling in the, because there are some remaining issues, important issues, not technicalities, but conceptual problems. So when I say our formalism can be used to propagate stuff behind the black hole horizon in the setup, I'm being a little bit lenient in what I mean. I'm just offering some observations about how this formalism would work if developed properly in this setup. Now, there is no difference in our framework between a two-sided black hole and a single-sided black hole. So you could run the machine that I will present, in principle, you could run it for a single-sided black hole, and you can still get the same thing. The thing that's clearer in the two-sided setup is this conceptual puzzle that this commutator problem with the left, right? Now, the same puzzle exists in single-sided black holes, but it's a little bit more complicated to set up, because you have to essentially, for example, you have to the proper way of setting up this puzzle in single-sided black hole is to evaporate the black hole for long enough, so that you know, you develop an island in the interior that's now in the entanglement wedge of the radiation. So if you evaporate the black hole for long enough, you again have the same issue, in that a CFT degree of freedom that you send into the interior after a finite proper time is not encoded in the CFT anymore, but now is in the entanglement wedge of the radiation, which could be, you know, a completely separate system. You know, it could be you may have dynamically decoupled the radiation and the CFT by the time you know, that you're interested in. So the same issue of the commutator appears there as well. So it's not a feature of just a two-sided black hole. It's a feature of VR equals EPR, let's say. In any situation where you have VR equals EPR, two entangled systems that are supposed to somehow have a common shared interior, you run into the same kind of conceptual puzzle as this. This is, by the way, the puzzle that Marolf and Wall first talked about in the context of VR equals EPR, at least a version of that puzzle. So it's the question, in what sense the shared interior of two entangled but decoupled systems is operationally meaningful. You know, to what extent I can probe it by falling in, or what are the, you know, what's the proper way of understanding this in falling experience? Yeah. Anyway, so this was a confusion that we had, and this is kind of what motivates the general kind of pursuit. But of course, you know, the question of how to extract physics in an internal reference frame is of interest regardless of black holes. It's the question of bulk reconstruction. So what we essentially, our approach to this bulk reconstruction was the following. It's kind of 3 steps. The first step is to choose some sort of physical probe that is well behaved and with nice properties, which will play the role of our observer in the bulk. Then evolve the system. The probe will just, we will assume the probe will propagate along some kind of classical trajectory in a semi-classical spacetime. At least for a sufficiently good set of probes, this is how it works. And then identify a prescription in the CFT, sort of universal prescription, that extracts some kind of physics in the reference frame of the observer. For example, how much proper time it passed between 2 kind of moments along this world line, how much energy that probe measured, and ultimately how to propagate degrees of freedom along that world line. Yeah, so this is kind of what our approach was, and I can say a few words about how it works, unless there are questions. Yeah, maybe I should like just present the basic setup, which is we chose as our observer a black hole. The probe that we use to explore spacetime, we chose it to be a black hole. In particular, the way we did it is we kind of introduce a black hole. So if this is the system, this side here is the system that we're interested in exploring, our holographic universe. We introduce a reference. It's not terribly important, but we introduce a reference and we entangle the system and the reference in the thermofield double state. So that introduced in our system some sort of static black hole at the center of ADS. And then we thought but now we want to kind of use that probe as an explorer, right, in whatever universe we want. So what we do is we first act with some ADS translation to get on the system side to kind of move that probe out of the way, move it towards the boundary. And then we act with some unitary on the system side, whose role is to generate whatever background we want to explore. Namely, if you have a particular state that you like, that you want to explore, which is what this U system creates, you just first put the system in the thermofield double, move the black hole out of the way, far away from the black hole, the spacetime, you know, the black hole's influence will, the black hole's back reaction will become negligible if we're far enough away. And then we act with the unitary of the system there to essentially create the state we want, and then we allow the system to evolve. So that's kind of our setup. You just introduce a black hole somewhere near the boundary and just let it propagate and see what you can get out of this. So one question that is often asked at this point is why a black hole? Why not choose, I don't know, some sort of some particle, some coherent wave packet that propagates along a world line? So there's many reasons for that. One reason is that the black hole is guaranteed to kind of be semi-classical. The other one is that I know how to introduce the black hole in a kind of very nice and economical way, using this kind of, by putting the system in a thermal state, essentially. In this case, we tagged the black hole by entangling it with a reference. It also has, but most importantly, it's because of what I'm about to present, and maybe you already saw it in the talk. It's because of the fact that what I'm going to use, it's because of the following property, that the modular Hamiltonian of the black hole acts geometrically in its neighborhood, generates that kind of boost isometry near the black hole horizon. And that's important. That's kind of the key idea that will allow us to relate this modular clock, with namely the clock generated by the density matrix of that state, to a geometric clock in the bulk that will be the proper time clock. That's kind of something that is, I have no reason to expect, let's say, if I just introduce some sort of particles. The modular flow of a bunch of particles, even in a coherent state, is not clear why it should have a geometric meaning. But for the black hole, it does. So somehow the black hole's modular Hamiltonian seems to be special. What's special about it? We can talk about this. It's an interesting question, actually.
Hi, I'm confused because, I mean, you don't have black holes on the boundary. I mean, you don't have black holes in the CFT, right? So are you saying you're creating a black hole in the boundary and sending it, or maybe...
I don't know. I create a black hole in the bulk, but near the boundary. By the near the boundary, I mean I create the black hole in the center of ADS, and I just translated it far away from the center by acting with a translation, so that it's a black hole that that I started out far out towards the asymptotic boundary, but it's still a bulk black hole.
But I mean, also massive particles and black holes don't reach the boundary, right? I mean, in ADS.
Yeah. So no, I'm changing the boundary state. I'm just exciting the state in a particular way that describes. So all I'm saying is that this state over here, between the system and the reference, describes a pair of entangled black holes, one in the reference, one in the system, where the system black hole is located, kind of off center. It's kind of a black hole that I send in from over here. It's not a static black hole sitting at the center, but rather a black hole that starts out on the initial slice. It starts out somewhere far out, and it will propagate along approximately along some kind of geodesic in the bulk.
But I mean, does the initial commutator paradox in quotation marks arise in this case also, because you're not starting from a boundary excitation?
So this commutator puzzle is a property. Okay, maybe I said too many things, and so this black hole I'm using here is not the same as the black hole that I used earlier.
I know, but I mean, so the original commutator paradox had to do with starting with some boundary excitation and literally on the boundary and evolving it towards the bulk and having it, letting it cross the horizon, right? But now you're saying you're not starting from a boundary excitation. You're starting from close to the boundary, but not at the boundary. Am I getting it wrong? Or?
Well, so, okay. So let's, there is a version of the commutator puzzle, I guess, that you can formulate in this setup as well, by kind of thinking of this background of a Rindler wedge in this background, right? So you can think of this as, again, the right and the left analog, and I'm introducing a black hole on the right. So the proper way of phrasing the paradox is the puzzle is as follows. You introduce that observer, that physical probe, in the way I did over here, and then you take some kind of operator on the right. I'm sorry, my figure is really bad right now. You take some kind of operator on the right, which you can entirely reconstruct by using ordinary Rindler reconstruction on the right boundary. So it is a right boundary operator, and then propagate it along that trajectory until you have crossed that horizon. So that would be the version of the commutator puzzle here, I guess. That you start with an entirely right Rindler wedge operator, which you propagate along this trajectory using whatever rule I'm about to talk about. And then you kind of now can receive signals from the left. Of course, in this case, the puzzle is not, it's easy to dismiss the puzzle because you say, well, there is a global Hamiltonian that I can use to propagate the system forward. So there is no deep puzzle in this case, and I will agree with that. It is kind of like a cartoon version of what the real puzzle is, in the situation where a notion of a global Hamiltonian is not available. But it's kind of, captures the same kinematic features, I guess, as the actual puzzle.
Okay.
So the probe is introduced in this way, and then so I don't know if that clarifies the question. I shouldn't repeat myself too much.
Yeah, thank you.
Lampros?
Yeah.
I just want to understand a bit better what the puzzle is. So isn't the solution just that the U that you're constructing, this operator that does this translation along this world line, it just has support on the left and the right wedges?
Yeah, but why and under what conditions?
Yeah, so I think a very simple example, maybe you already mentioned it, but would be, if you go back like to the slide where you showed this, you could, almost everything that you said, maybe, this one, we could recast in flat space and think of this as the Rindler wedge, right? So suppose that this black solid line would be a boost, but a boost to the left, not to the right. Mm-hmm. We know what operator does that, right? But that operator has support also on the left, because it's a boost with respect to a different wedge, right?
Yes.
So we know how to construct that operator. We know how it looks. And so am I getting this right? Is this like a baby version of the puzzle?
So, okay. So here's the difference between quantum field theory and this setup. And that's kind of the key difference. The operator that moves me along this, this could be like an null trajectory, right? Just for simplicity. It's a translation. It's the action of an appropriate momentum operator, right? In QFT, the algebra of operators and the stress tensor of the theory is an input. It's something that we start with. It's you don't have a question of what the operators are in a quantum field theory. You define your theory by having the algebra of operators given to you. In this setup, what we are given is the boundary description. So what I'm trying to ask here is, what is the definition of the bulk stress tensor, of the appropriate bulk stress tensor or translation generator that takes me behind the black hole horizon? If I have access to the translation operator by definition, like in quantum field theory, I can construct the translation along any trajectory I want. That's why this is not, this is not really a meaningful question in quantum field theory. I can just take stress tensors and appropriately, use them to translate along any trajectory I like. That's why we don't ask this in QFT. But here, we don't have an independent definition of the bulk quantum field theory. So we only have a definition of the boundary quantum field theory. So what is the definition of this translation generator that shifts us past the horizon? That's kind of the question I'm trying to ask. And my approach is to kind of say that, well, if you had a way of introducing a well-behaved probe, and you understand what is the clock of that probe, then that clock is effectively a translation. So if you can define the clock of an internal excitation, then you have defined what this translation is. But it's a matter of definition, that we don't have a priori the definition of the bulk stress tensor to propagate things.
Okay, so it's an ADS-CFT question, really.
Yes, it's an ADS-CFT question. It's a question about holographic reconstruction. Yeah, it would not be a puzzle if you do it in quantum field theory, because T mu is given. Yeah.
Okay, thanks.
No, that was a good comment, because this is, I think, one of the points that sometimes it's hard to come across. That what we assume as input, and we do not assume as input the knowledge of the bulk QFT operators. If we did, then there is no puzzle. I can just do what I usually do in quantum field theory.
Lampros, can I ask you, I'm still confused about the choice of a black hole as an object to probe this geometry, because you are also introducing another horizon. Mm-hmm. And, I'm puzzled because let's suppose, like, when you define the atmosphere operators, I would expect that these world lines would fall into that at a time scale that is of order of the inverse temperature. So essentially, this tube that you draw, like, it would shrink in time. So
okay, so it's a little confusing to draw diagrams, Penrose diagrams with two black holes, but you know, a black hole propagates in the ambient spacetime for as long as its size is smaller as compared to the features of the ambient spacetime. It propagates approximately like a probe, it propagates along a world line. Now that's what the black holes in the sky do, right? You should be thinking about the apparent horizon of the black hole. You define the black hole in terms of their apparent horizon. Black holes in the sky, as long as they don't get too close to stars or other black holes, and you know, you have kind of non-trivial astrophysical processes, they propagate like, you know, like any other celestial object does along world lines. So that's kind of the approach that I'm taking here. I'm introducing a black hole whose features will be smaller than the features of the spacetime I'm trying to probe. And I'm just using that that fact, and I'm saying I just want to something that I have not explained yet, but I will use the fact that and maybe I should just jump to it. I will use two facts. One, that the modular Hamiltonian, defined as the logarithm of the state of the CFT after I trace out the reference, generates this boost isometry close to the black hole horizon. And the second, that this boost isometry gets glued to the, if I zoom out where the black hole becomes a probe, is morphing into the proper time translation of the ideal kind of world line observer. So if you zoom out, the black hole looks like a point, right? And the space-time around this looks approximately flat. There is some kind of local killing isometry that is a local isometry of the space-time and preserves the world line. But if as I zoom in, as I start going closer and closer to that black hole, eventually I start seeing the back reaction of you know, the non-trivial geometry of the black hole background, and this killing isometry becomes that boost, which I know how to describe with modular Hamiltonian on the boundary. So this is kind of what the picture that I'm going to exploit. But yeah.
So, for example, in this picture, I would be worried that in the bottom, this line is a geodesic, but in the top is not. Right, because
no, but it kind of is, right? Kind of, you know, kind of close your eyes a little bit, kind of zoom out of the picture, and the black hole will look like some ordinary object traveling in the sky. And at this level, again, if you don't get too close to things that depend crucially on the fact, on the features on the precise features, local features of the black hole, it will look like an object that's traveling along a geodesic, right? This is how you would. It's confusing if you try to kind of picture it in a diagram the way we usually do. We don't usually, but if you, yeah, I don't know if that comment actually makes it somewhat clearer.
Just maybe a side comment and question. I mean, is there a relation to this, like the construction of mirror operators that are supposed to commute in some like code subspace, but they stop commuting, and like they're supposed to resolve this puzzle and help you reconstruct behind the horizon and so on?
Okay, so Mert, you're going straight to the million-dollar question, and namely how you use that framework for actually seeing behind the black hole horizon. So So, okay. So if you trust this, okay, I guess I have not really given you details of the formalism yet, but if you trust that this modular flow to some approximation that I haven't really discussed yet actually does propagate you in proper time, and if you convince yourself that this is the case, then the way that you would use this framework in the context of this two-sided puzzle that we're discussing before is something like that. So you will start with a thermofield double between left and right, and you would introduce this black hole on the right by entangling it with a reference. And how would you do this? Well, imagine starting with a thermofield double between left and right and some kind of reference state of the reference, and then you act with some kind of unitary that entangles the right and the reference. But this does not touch the left. I'm introducing a probe, as I said, by only kind of using right degrees of freedom. So now you have some kind of entangled state. I'm not giving you details for what this O, R, and O reference are, because I don't know the details of that. It's actually making this kind of procedure precise is ongoing work between Pingao, actually having like a toy example of this that's under control, and that's what we want. But let's assume that you know any entangling procedure would look like that. And then you trace out and according to what I kind of schematically explained, and hopefully you watch the talk for the details. The way to construct this proper time Hamiltonian is to take the state, trace out the reference, and construct the logarithm of the corresponding reduced density matrix, which will give you this modular Hamiltonian for the probe, and then simply take an operator over here and then conjugate it with this modular flow. Now, this, just as a word of caution for those who did not watch the talk, this is supposed to accurately describe the proper time propagation as long as nothing disturbs my black hole atmosphere, as long as nothing falls in my black hole. If something falls in the black hole, then this doesn't work. There are some corrections that I have not discussed here, but I'm happy to talk about it. But let's assume that for now this is the case. Then this operator is some kind of operator translated by some proper length tau along this trajectory, and eventually it will be something behind the horizon. So this is kind of a very simple way of looking past that black hole horizon, assuming this proposal works. Now, the reason why this two-sided puzzle is not a problem in this formalism is because if you take such a state and you trace out the reference and you act, how does this modular Hamiltonian I obtained act? You will find that it couples left and right because of the entanglement between left and right. This is just a generic fact coming from the entanglement between left and right that you can convince yourself for. Now, this does not answer whether, let me make a comment. This does not answer whether the coupling that you get in this case is the correct one, but you do get an operator that mixes left and right degrees of freedom. Now, whether it's the correct one, namely, the appropriate kind of geometric translation along that word line, it's something that is a subtle question, and I'm happy to discuss that. But just as a zeroth order kind of answer to this is that this prescription using the modular flow of the probe to propagate just does not suffer from this kind of conceptual issue, assuming you take this as the principle.
And
I had somebody make a comment earlier.
Right? Yeah, maybe I should have raised my hand. So this coupling between left and right is going to be there at all times, at all proper times.
Yes, but the same way that let's how should I say this? Maybe I should change pictures here. Forget about what this slide says. I just want to draw. The same thing is true for a Rindler decomposition of the vacuum, where you have the global Hamiltonian, right? The global Hamiltonian couples left and right Rindler wedges at all times. But if you take an operator over here, it will take some time for that Hamiltonian to actually mix that degree of freedom with the left, right? So the coupling is there at all times, but the flow of a particular operator will not necessarily immediately mix with the left. It will take some time based on the properties of that coupling that appears there.
Yeah, sure. Thanks.
Yeah.
Lampros, but why? Suppose I take the state in which a trivial example of what you're saying. So suppose I take the reference state to be whatever, and I take this unitary to be the identity. So actually I use the thermophile double in a tensor product with some other ancilla thing, right? So now you trace out the reference system. Basically that didn't do anything because they were in a direct product, right? So then the resulting modular Hamiltonian K here, isn't it going to flow? Well, it depends what is the state you chose to start with, but isn't it going to flow to the right rather than to the left?
Wait. So I maybe missed something important. If you don't, okay. The prescription is that you entangle the system with the reference in a way that produces a state with a thermal spectrum on the system side. The thermal spectrum is associated to having a black hole, having a probe that's a black hole. So if you don't entangle with the reference, then I don't know what, this modular Hamiltonian, I don't know what it does. Probably nothing, actually. Probably it's a very singular kind of thing because you have a pure state on the system side, right? It's just the global thermophile double state.
Yeah, but that wouldn't that flow look like a boost toward the right in this what I'm trying to get at?
You're thinking of the modular Hamiltonian of the right CFT only, where you've traced out the left. That's a different kind of object, though. Here I'm talking about so what we use in this formalism is the modular Hamiltonian of the entire left-right system after you trace out the reference which you previously entangled with it. So that's a different object, right? This is not generating the same flow. I agree that the modular Hamiltonian of the right will look like a boost about this in the exterior of the right black hole. The modular Hamiltonian of the left will look like this type of boost. Here I'm talking about the modular Hamiltonian of the entire system, namely the union of left and right algebras, that's coming from the entanglement of the whole system with the reference. In a sense, one intuitive way of understanding why this type of modular Hamiltonian couples left and right, that in this case, is the fact that when I start with thermophile double between left and right, you have some entanglement between the two sides. Then you act with this entangling unitary and you try to entangle the right system with the reference, but this inevitably entangles the reference with the left as well. So when you trace out the reference, you get a complicated system because the reference is now entangled with the entire left-right system in a kind of non-trivial way.
Right. Okay. Yeah. So maybe that was my question. Like, why do you expect that this is going to give you something that has some geometric meaning in general? It's going to be a very complicated thing that has support in a region that's growing and.
Yeah. Very good. Yes. Good. It is not a trivial question of whether this coupling has the right properties. There's got to be conditions for the types of states and the types of probes that allow for such for the coupling to be of the right type. So before I make a couple of comments on that, I just want to emphasize that the first kind of problem I want to address was in what sense there exists a coupling to begin with. In what sense the entanglement translates into a coupling. Now we're asking a much more fine question and difficult one, but important. Under what condition does this coupling has the right form? The reason why I expect that for these black holes, for these black hole probes, this modular Hamiltonian will have the right kind of coupling, is essentially that little argument I gave in support, briefly, in support of why modular flow generates the proper time, which was kind of an abstract argument. To the degree that I can trust that the modular Hamiltonian generates a boost near my black hole's horizon, then I expect the flow to be the corresponding boost in the, I expect this flow to be associated to precisely this translation along the observer's world line. It is not an obvious question how you would exactly introduce from, step by step, how you would introduce a black hole entangled with a reference using in this two-sided setup, and how, but yes, so, but if you manage to do this because of this argument that I'm making over here, I expect that this reasoning would just carry over and would give you the right translation generator. Showing this is the case is actually part of ongoing work, in that, can you actually do this? Can you start, let's say, in SYK or some kind of simple system and appropriately entangle the right with the reference in a way that mimics this kind of probe that I'm using here? Construct the modular Hamiltonian of that thing and show that it actually acts in the expected way. This is not a trivial question, I can tell you that. But because of this kind of abstract argument I'm making here, the relation between this K and the geometric boost near the horizon, I expect that there is a hope that the answer is yes, it does the right thing under potentially some conditions.
Yeah, Lampros, I have a question. I think you, just try to answer that very same question. You wanted to give an intuitive argument of why tracing out the reference state will couple also bear some information with the left CFT. Yeah, I'm still a bit confused. So I think at some point you said that whatever probe you are introducing may be a, some particle or a thermophile double state near to the boundary. It can be written down solely in terms of the right CFT. Right.
The operator itself, yes.
Yeah. So, this is a CFT question. I can even forget about bulk. I have that state which you wrote in one of the slides. So there is a coupling between two CFT states. Both are CFT states, right CFT states. And you are claiming that in this particular coupling between two one right CFT state and one reference state, which has nothing to do with the, the original thermophile double state, the big one. I get part of the left CFT. I get some information about a completely different CFT. How can that be? Then it must be true that this thermophile double state is not really generated by just the right CFT state, isn't
it? The thermophile double is not generated by just the right CFT state. You have two CFTs in a particular entangled state.
No, by thermophile double here, I mean the dot near the right boundary. That
right. But so the point is, so entanglement has weird properties, right? If you have two systems that are very entangled with each other, and you try to entangle one with another one, because of the monogamy of entanglement, you may actually end up doing something very non-trivial overall.
But do you agree that this state that you wrote down, it's just a entangled state between two CFTs, right?
No, actually, no, absolutely not. No, this is an entangled state between three CFTs. There's left, right, and reference. I started with a very entangled state between left and right. Then I try to entangle one of my right CFT with the reference. But in the process, I'm producing a entangled state of all three systems that is complicated. Right. It is not true that this is, that's kind of my point here. I guess that's kind of the underlying issue here, that this does not produce, this does not, the naive picture that, by acting with that unitary will just entangle some right degrees of freedom with the left is not true in general. In fact, you can actually, so here's a little exercise that you can play with. You can actually try to, formally use this argument and trace out the reference in this case, and convince yourself that the modular flow you get for the system involves coupling terms between left and right.
But would you agree with the fact that this little dot near the right boundary, which is the TFD state in your case, that I can construct entirely in terms of the right CFT, just by like HKLL or something?
Yeah, so this little operator here is a right operator, and I can entirely construct it in terms of the right. But the operator I'm using to propagate that guy, namely this K, is not a flow that that kind of maps the right algebra into itself. It's a flow that mixes right and left.
But the K is obtained by tracing out zero reference, which is
no. Okay, I think so. I think you. So here's the thing. There's this guy acts non-trivially on the right and the reference and entangles the two. Right. This is kind of a unitary that.
I see.
So when I trace out the reference, I'm not tracing out a system that's in a product state. That would be trivial, of course. Yeah. Okay, I agree. Sorry. So yes, this is I'm first performing an entangling operation. So now the reference is in some complicated entangled state with my full left-right system. And it's in that state that I trace out the reference and I get a flow on my system side.
Okay. Yeah. Thanks. I think it clarifies. Yes.
Yeah, of course.
But can I play devil's advocate real quick?
Yeah, please. I love that.
Okay, so as far as I understand, you have this puzzle. You want to understand how to do some propagation that involves in both the CFTs, left and right, when they're a priori not coupled. So you introduce a third system, entangle with the third system, then trace it out, and now you're left with the density matrix that, of course, by construction involves the left and right of your first. And now you take the log and you evolve with that. So that is also, as an operator, going to evolve both by construction.
Yes.
So so you've introduced some way of defining this operator that involves first introducing a third system, then getting rid of it.
Yes.
And then you say, okay, maybe this thing is the thing that propagates things on the right into the black hole. But I mean, unless you can construct that explicitly, I still, I guess, don't see why that's, for example, better than just using the H left plus H right type evolution, which also involves both systems.
Yeah, but H left plus H right will not couple left and right, right?
Yeah, it won't. That's true, but.
So just to give a brief comment on that. So, okay, so good. That's actually an important question, and let's discuss this. What is this good for? Like, why care? So, okay, why care? So the first part, as I mentioned earlier, as a response to a comment by Ignacio, we don't have an independent definition, or we don't want to assume an independent definition of the type of Hamiltonian that would take this bulk Cauchy slice, here, and kind of move it in the interior. We don't want to assume that. if I assume I know the spacetime, of course I can do this, right? If I assume that I know the QFT on that spacetime, I can certainly construct such a thing. And there is then no kind of, or even along any slice alike, there is no puzzle there. You can just input usual QFT machinery to do that. So we don't allow ourselves access to that. We want an operator that's defined directly on the boundary. That's defined by the boundary principle. So the first advantage of using the first good thing about this observation I'm making is that I'm giving you a definition. The object I'm using is well defined in the CFT directly without, you just introduce a probe. Your probe is a little thermal state, a little black hole in the bulk, a little thermal state in the CFT, appropriately introduced. And there is no ambiguity about how you define this modular flow. It's just a well-defined object. The second important thing that still that story by itself would be kind of vacuous if I didn't have an argument in the bulk for why this should correspond to this geometric translation. And the argument, I gave you a very kind of formal high-level argument, but you can actually explicitly check that this modular flow does do the right thing, let's say, for black holes propagating in ADS along arbitrary worldlines. And that's important. You need some kind of, by the nature of this discussion, I did not kind of dive into these details in this today, but you can, we would not trust this prescription until we had a correct computation of the time dilation between two arbitrary worldlines in pure ADS, let's say. And the thing is that this prescription does work in that case. It does give you, we can debate why, but it does, in these simple setups where you can compute this, it does give you the right thing. And there exists a formal argument for why it does so. So I think these two statements combined is a partial answer to what you said. The existence of a very clear definition on the CFT without any reference to the bulk, that's important, only reference to the state and the probe I'm using, and then the existence of an argument under certain conditions that for certain probes and for certain states, that modular Hamiltonian is expected to have a geometric interpretation in the bulk. So that would be my answer to your question. Why care? But I totally sympathize. Yeah, go on.
It was more like I think the surprise for me is that I would imagine the process of, say, propagating something into the black hole. I wouldn't expect to need to produce an additional reference system to do that. And
yeah, right. So you see, so the reference system is not terribly crucial. It's kind of convenient, but it's not terribly crucial. What you really, I think the same story would work if, although this is harder to do. The same story would work if you simply kind of took if you took some kind of object and traced out its microstates. If you took it if you just construct the black hole from collapse, right, and you just coarse-grained and you obtain the coarse-grained modular Hamiltonian, the modular Hamiltonian associated to somehow capturing your ignorance of the microstate in which the collapsed black hole is in. The expectation is that the same thing would work there. There's no deep difference between these two setups, at least in my mind at this point. So I don't think, although you already understand that doing that, actually constructing that state where I collapse a bunch of degrees of freedom on the right into a black hole is a very difficult thing to do, and it's probably equally difficult to solving the problem. So so the reference is kind of a convenient device, but the argument would be that somehow it doesn't. It's kind of like this is kind of a toy version of the actual problem, which is you form some kind of object, you have complete ignorance about the microstate that it's in, except for how much energy, you know, that thing has asymptotically, and some kinematic variables. And then you declare complete ignorance about its microstates. So now you have some kind of reduced state describing the universe without that object, where that object is kind of traced out. And that modular Hamiltonian is what you would use in that case. Now, do I know this is true? No, this is speculation, of course. But you know, I totally sympathize with the need of an explicit example of what I'm describing here, and that's why I'm working it. But it would be nice to have, like, you know, a concrete kind of toy version that does the job correctly.
Lampros, one more question. So
yeah,
if
please.
I consider the same type of system, let's say it's quite unrelated, or okay, somewhat unrelated question. So if I consider ADS3 Rindler, and I have this, you know, left CFT, right CFT, then I know that I can consider, let's say, K, what, KR and KR bar, and then I can add them and subtract them, and I can construct, hope I'm remembering it correctly, I can construct some modular operator that, you know, flows it in modular time, and modular also another set of operator which translates it along the angular direction in this case.
Yes.
So everything here stays within the right CFT. Let's say, yes, I'm working only with combinations of KR and KR bar. And then can I construct some operator which takes me from, you know, left to the, or right to inside the horizon in this simple case?
That's a very good question. If you have another way of constructing that operator, this is good progress. This is my answer, my kind of approach at this point. There are other possible ideas that you can use for constructing this translation. I should say this is not the only way that you can ever probe the interior. This is just a way that seems to work, you know, within its regime of validity. So this is one answer to your question. This K constructed this way is an operator that seems to be doing the right thing. But you know, if there's another way of constructing a flow that mixes left and right by some other principle, perhaps using properties of this, of, you know, the two exterior modular Hamiltonians, that's definitely an interesting question to know the answer to. I don't know. Well, that's yeah, there exists another approach, but it essentially boils down to the same object at the end of the day. You could. Yeah. Anyway, let's. I guess maybe I shouldn't comment on that.
Okay.
But yeah, that's the question that we're trying to answer, right? And you're right. This is kind of the point of this.
So once again, here it's happening because you had this entanglement between a right CFT operator and the reference state operator, reference system operator, and then you traced out the.
Yes, so this process naturally kind of gives you a flow on the original system that preserves the full algebra of left and right, but not the individual left and right algebras. That was the benefit of this approach in this case. And okay, and as I was commenting in response to Tarek's question, it also seems to be doing the right job in the bulk, using that intuition. Semi-precise intuition about this modular flow being associated to boosts close to the black hole horizon. That's not exactly true, and that was reflected in our formalism with Daniel, where there are corrections to this modular flow if you really want to describe boosts, if you really want to describe this geometric flow. And there are other corrections that have not been figured out yet, and it's part of our discussions currently. So take these statements that modular flow generates the boost or proper time flow, take it with a grain of salt. It's true with certain assumptions that you should look in the paper for. It's not an entirely settled question. What is that geometric generator in general? But in some situations is K.
Okay, thank you.
Can I ask you about those conditions? I will also read it in the paper.
No, yeah, we don't answer the question in the paper. That's why we're working on it. So,
could you go to this slide? I just wanted to understand how do you the slide about the, I think what you're calling the black hole modular flow. This
here?
one. Yeah, this one. So this is what you were talking about, what you referred as the second point of this construction, right? The second thing you have to assume or understand. So here, how are you defining these lines?
Oh, so these are just Schwarzschild times.
So these are killing.
No, these are you're right. So these are constant Schwarzschild times. So
okay, that's geometry. So then how do you, what is the rule to find the purple lines that you associated to K? Is it that you do quantum field theory?
Right, yes. So good,
and you trace out part of the Hilbert space, or
right. So this is good. So the question, by the way, feel free to leave whenever you want. I noticed that it's 15 minutes past, so I won't be offended by anyone leaving. So the argument for why K is related to this boost generator is the following. So I keep defining K as minus log of rho, but a more appropriate way of defining K is in terms of this KMS operator. A KMS operator, namely, that when you take the exponential of this e to the minus K, and you compute its matrix element with two states, which you obtain by acting with some operator phi2 m psi or phi1 psi. Then this matrix element is given by this correlation function, where the order of these two operators is inverted, is reversed, is changed. This is what this operator, this is how it's really defined.
But I thought rho was defined on the boundary theories, on the CFTs.
But each of these operators is also a boundary CFT operator, right?
So then why are you drawing a bulk purple arrow?
We didn't get to the purple arrow yet.
Okay.
This is the definition of K in the CFT.
Agreed. Okay.
So this is how it's defined, as this KMS rotation. It's a rotation. It's a symmetry of the state, and it's generated. You can define, this is the definition of K. Instead of log of rho, you can define it like this. Okay. Now, Now, this is the definition of K on the boundary. Now, the argument that relates this to the boost close to the black hole is the following. Close to the black hole, if you fire the atmosphere is in a local thermal equilibrium. This, to the extent that this is true, of course, you can disturb that local equilibrium by sending something in, but the system will thermalize again because of the quasi-normal decay of the propagation of these excitations. So these, whatever disturbances you made will die off exponentially in time. The system will equilibrate, and again it will come back to local equilibrium. So if the atmosphere is in a local thermal equilibrium, this means that if this phi2 and phi1 that I used here are operators within the atmosphere, by definition of what thermal equilibrium means, they will have to be invariant under a KMS rotation, under a weak rotation of the time with respect to which they're in equilibrium. But that time is precisely that boost time close to the horizon. So the boost killing vector, the weak rotation of the boost killing vector is precisely the KMS operator as it comes from the requirement that the atmosphere is in thermal equilibrium. But K is the KMS operator for the entire for all operators. So for those operators close to the horizon, K and the Schwarzschild boost are the same. So KMS is the exact. So K is the exact KMS operator for all operators in the theory. The weak rotation of this Schwarzschild boost is the KMS operator for the near horizon operators, assuming this thermal equilibrium, and therefore the two operators K and the Schwarzschild boost act the same on near the horizon. That's the argument. If my atmosphere is in local equilibrium. At intermediate times, when particles go through and kind of disturb the atmosphere, that's not true. The modular Hamiltonian is complicated. It's not a geometric flow. It has non-local. It generates a non-local flow. But because the system equilibrates, all these non-localities die off as well. So in the end, it becomes again a geometric flow later on. This was a little bit convoluted. I don't know if it made sense, but it's definitely explained in more detail in the paper. But there's a formal argument to be made, with some assumptions, of course, for the connection between the boundary K on the boundary as defined from boundary principles and the Schwarzschild boost in the bulk as defined by bulk principles. There's an argument to be made that these two act the same near the horizon.
Yeah, sorry, it's already 20 minutes past the hour, so
yeah,
maybe it's a good time to wrap it up, unless there are last minute comments.
Yeah, up to you guys. I'm up now, so I'm happy to stay here for another 3 hours.
Have you had your coffee?
Well, you know, this conversation is working a little bit more than caffeine, I have to say. It's more effective. Thanks for coming, by the way. I appreciate you being here and asking questions. I didn't know how this went, but I think, but at least on my end, there was enough interesting discussion, and I appreciate your questions and interest.
Okay, so then let's thank Lampros and thanks for the discussion.
Yeah, thank you. Hope to see you in person sometime not too long from now.
It's gonna happen.